Good afternoon, everyone, and a pleasant welcome to all the students for the chemistry webinar. Myself, Mrs. Sridevi Polu, Principal TSMS Pudu, is privileged to welcome the speaker of the day, Dr. B. Sampath Kumar Garu, PGT Chemistry from TSMS Shankarpatnam, Karimnagar district. And dear children, in our previous session, we have started learning the classification of elements, isn't it? What we call as the periodic classification of elements and the periodicity in properties. And in our last session, Sir has explained you regarding the salient features of long form of periodic table. See, let me briefly explain you what are the salient features. See, the horizontal rows are called as periods and the vertical columns are called as groups. There are 18 groups in the periodic table and 7 periods. And he has clearly explained you regarding the division of elements into blocks, how they are divided into blocks, and then depending upon the properties into what types they are divided. And today, Sir is again here to explain you regarding the classification of elements into 4 blocks: S block, P block, D block, and F block. Dear children, let me tell you, if the differentiating electron, see what is a differentiating electron? The last electron present in an atom is called as a differentiating electron. If the differentiating electron enters into the s orbital, these elements are called as s block elements. Like that, they are called as P block, D block, and F block. And depending upon the chemical properties, they are again divided into 4 types. What are they? So are you curious to know about this all? So let us welcome Dr. B. Sampath Garu, PGT Chemistry from TSMS Shankarpatnam. Good afternoon, sir.
Good afternoon, madam.
So please welcome, sir. So today, what topics you are going to explain, sir?
Classification into blocks.
Yes, sir.
And classification into types.
Okay, sir. Okay. So I think children, this is a very interesting topic for you because all these are the fundamentals which you had to learn before learning the other topics in the chemistry. So let's invite sir. So thank you, sir.
Thank you, madam. Thank you. Good afternoon, children. Today we are going to deal with the chapter classification of elements and periodicity properties. Intermediate first year chemistry, chapter 2, session 2. This is Dr. B. Sampath Kumar, PGT Chemistry, TSMS Shankarpatnam, Karimnagar district. My subject coordinator is Srimati Polu Sridevi Madam, Principal, TSMS Pudu, Vikarabad district. Children, these are the topics we have discussed in the last session. Need to classify the elements, genesis of periodic classification, Doberan's priors, Newland's law of octaves, Mendeleev's periodic law, modern periodic law, long form of periodic table and salient features, nomenclature of elements with atomic number greater than 100. And this is my today's session. The session overview is electronic configuration of elements on the periodic table, electronic configuration in periods, electronic configuration in groups, electronic configuration and types of elements, that is S, P, D and F blocks, S block elements, P block elements, D block elements and F block elements, classification into types, inert gas elements, representative elements, transition elements and inner transition elements. Now the other chapter is metals, non-metals and metalloids. So children, let us see one by one. At the electronic configuration of elements on the periodic table, what is the electronic configuration? So already we know from 9th and 10th class onwards, the electronic configuration is nothing but the distribution of electrons into orbitals. What children? the distribution of electrons into orbitals. What are the orbitals? S, P, D, and F. So the distribution of electrons into orbitals of S, P, D, F of an atom is called its electronic configuration. Let us see. Here for example, sodium is atomic number 11 and its electronic configuration is 1s2, 2s2, 2p6 and 3s1. So here we fill the electrons in the orbitals. Increasing order of orbitals, we have filled the electrons. See children, we know very well the molar diagram. In 10th class we have learned. Here the orbitals are arranged in the increasing order of their energies. And in these orbitals we have to fill the electrons so that we can get the electronic configuration of any element. So this orbitals, increasing order of orbitals is arranged on the basis of n plus L rule, means which is having less n plus L value, that is with less energetic, and which is having more n plus L value, that is having more energetic. For example, here 2s and 2p orbitals are there. In this 2s and 2p orbitals, which is having less energy, which is having more energy. See, let us see the n plus L value for this 2s and 2p. Here, what is n? N is the principal quantum number. And what is L? L is the azimuthal quantum number. Here, for S subshell, the L value is 0. For P subshell, the L value is 1. For D subshell, the L value is 2. And for F subshell, the L value is 3. Now, if you want to know the energy of these two orbitals, if you want to compare, first we have to see the n plus L value, which is having less n plus value. So let us see. Here the n is equal to 2. Here the s orbital. S means here, what is the L value for s subshell? 0. Means 2 plus 0. Here 2 plus 0 means 2 only. But here 2 plus here P. P means P subshell means L is equal to 1. So here for n plus L value, here for 2p orbital is 2 plus 1, that is 3. Here 2 plus 0, here 2. So this is having less n plus L value and this is having more n plus L value. That's why here that these are arranged like this. Here we have to start at the top right side, means from here onwards we have to start. Here 1s is less energetic than the 2s and which is less energetic than the 2p. So like that we have to arrange from top right to bottom left. So these are the orbitals in the increasing order of their energies. So in this, if we fill the electrons, that will come the electronic configuration of an element. The maximum electrons filled in the s orbital is only 2. In p orbital is 6. In d orbital 10 and in f orbital 14 electrons. Now, location of an element in the periodic table. Children, how can we locate an element in the periodic table? That is, in which group or which period or which block it belongs to. So that is based on the electronic configuration. Now let us see. An element's location in the periodic table reflects the quantum numbers of the last orbital filled. See children, here the last orbital filled. In the electronic configuration, the last orbital field, based on this last orbital, we can locate the element in the periodic table. Let us see. For example, here sodium electronic configuration is 1s2, 2s2, 2p6 and 3s1. Sodium atomic number is 11. Here 11 electrons came, 2 plus 2 plus 6 plus 1, total 11. Here the last electron is in 3s1. So this is the electronic configuration of sodium. And this is the valency electronic configuration of sodium. 3s1 is the valency electronic configuration of sodium. Now this valency electronic configuration is 3s1 like NLX. So already we have learned NLX in the 10th class. Here N is nothing but here 3 and here S nothing but like L. And here 1 electron is nothing but like X. So this 3s1 valence electron configuration 3s1 is same like NLX. Based on this 3s1 valence electronic configuration, we can predict the location of the elements. Let us see here. NLX, in NLX, n denotes the principal quantum number, that is period, and L, it denotes the azimuthal quantum number, that is block, and X denotes the number of electrons in an orbital. It also refers to group. So by seeing the X value, in which group it belongs to, we came to know, and by seeing the n value, which period it belongs to, we come to know, and by seeing the L value, means which orbital, we can easily predict the block in which it belongs to. See, for example, sodium. Here the atomic number of sodium is 11, 1s2, 2s2, 2p6, 3s1, and this 3s1 valence electronic configuration, if we observe, it is like NLX. The n value is 3. The n value refers to period. That's why this sodium belongs to third period. And this L refers to block. So therefore, this is the 3s1. That's why it is S block element. And this 1 refers to group. Here this is like X. This refers to group. That's why here sodium belongs to first group. So like this, children, by seeing the valence electronic configuration, we easily predict the element location. Means in which period it belongs to, which group it belongs to, and which block it belongs to. And now next, children. So here electronic configuration in periods and groups. See, children, a critical observation on the long form of periodic table suggests that the number of elements in each period, is twice the number of atomic orbitals. See here, children, in first period, actually 2 elements are there. Here, hydrogen and helium. And in first period, how many atomic orbitals filled? Only s orbital. Means here only 1 orbital is filled, but in 2 elements are there in the first period. So the number of elements in each period is twice the number of atomic orbitals, because 1 orbital is there, 2 elements are present in the first period. So like that, in second period, totally 4 orbitals are there and 8 elements are present. See here, 1s, this 2s is the 1 orbital, and here 2p orbitals are 3, 2px, 2py, and 2pz. So totally 4 orbitals are there and 8 elements are present. And next, the period number correspond to the shell number. See here, second period elements all contains only 2 shells in their atoms, and first period elements contains only 1 shell. This third period elements contains 3 shells. So like that, the period number correspond to the shell number. And the next one is, each successive period is associated with filling up of the next higher principal energy level. See, children, here in the first period, here n is equal to 1. In second period, n is equal to 2. In third period, n is equal to 3. So like that, each successive period is associated with filling up of the next higher principal energy level. Now coming to the electronic configuration in groups. In groups, elements present in the same group have similar electronic configuration and have same number of electrons in the outermost shell. See, children, here the first group elements are having only 1 valency electron or outermost electron. See here, 1s1, 2s1, 3s1, 4s1, 5s1, so like that. For coming to the second group, here 2s2, 3s2, 4s2, 5s2, like that. So here the elements present in the same group have similar electronic configuration and have same number of electrons in the outermost shell. Now this is the general outer electronic configuration in groups. Let us see, children. Here total groups in the periodic table. Here 18 groups are there. 1, 2, 3, 4. So like that, up to 18 groups are there. In each group, let us see the general outer electronic configuration. For first group elements, the general outer electronic configuration is NS1. For second group, it is NS2. For third group or 13th group, it is NS2NP1. For 14th group, NS2NP2. So like that, for 18th group, it is NS2NP6. So like that, where you see here, for first group, NS1 means for first group elements, only one valence electrons are there. For second group elements, two valence electrons are there. So like that, we can write the general outermost electronic configuration is for first group NS1, second group NS2. This first and second group both combinedly called as S-block elements, and the general outer electron configuration of this S-block is NS1 to 2. That is NS1 and NS2. So combinedly called as NS1 to 2. In the same way, for P-block elements, it is the general outer electron configuration is NS2 NP1 to 6. See here NP1, NP2, NP3, NP4, so like that NP up to NP6. So that's why NS2, NP1 to 6. So in the same way, the outer electronic configuration of D block elements is N-1, D1 to 10, NS1 to 2. In the same way, the outer general electronic configuration of here F block elements is N-2, F1 to 14, N-1, D 0 to 1, NS2. So children, here elements present in the same group have same number of electrons in the outermost shell. See, for example, I have taken the 15th group elements or 50th group elements. These group elements are having same number of valence electrons. See here, I have underlined here. Here 2s2, 2p3 means 2, 3, 2 plus 3, 5. Here also 3s2, 3p3, 4s2, 4p3, 5s2, 5p3, 6s2, 6p3. So all are having only 5 valence electrons. So here the group number is 5, 50A or 15th group. So elements present in the same group have same number of electrons in the outermost shell. Now let's see the next two, children. Here electronic configuration and types of elements, S, P, D and F blocks. See, based on the entry of the differentiating electron. What, children? Based on the entry of differentiating electron. What is differentiating electron? Here differentiating electron is nothing but a newly coming electron. So based on the entry of differentiating electron into the subshells, here subshells are nothing but the orbitals, children. S orbital, P orbital, D orbital and F orbitals. So elements are classified into 4 blocks. So what are those? Let us see. S block elements, P block elements, D block elements and F block elements. If the differentiating electron enter into S orbital, that is S block elements. If it enters into P subshell, that is P block elements. If it enters into D block elements, that is D subshell, that is called D block elements. And if it enters into F subshell, that is called F block elements. And this S and P block elements combinedly called as representative elements. And D block elements called as transition elements. F block elements are called inner transition elements. So let us see, children, one by one. So what are S block elements, P block elements, D block elements and F block elements? See, actually these S block, P block and D block, F block elements are here on the periodic table. Let us see. Here S block elements are towards left side of the periodic table. Here first year, second year group elements are for S block elements, and the P block elements from third year to 8th year towards the right side of the periodic table. And in between this S block and P block, here D block elements are there. So those are in between the S and P block elements, in middle of the periodic table, and under the periodic table, these F block elements are there. Now the S block elements, the elements in which the differentiating electron enters the S orbital of the outermost shell are called S block elements. So what are S block elements, children? The elements in which the differentiating electron enters the S orbital. of the outermost shell are called s-block elements. Here group 1 and 2. The group 1 are called alkali metals and group 2 are called alkaline earth metals. These belongs to the s-block elements. See children here group 1 and group 2, these belongs to s-block. These elements are located on the left side of the periodic table. Where these located children? These are located on the left side of the periodic table. The general electronic configuration of s-block elements is NS122. So this is the general electronic configuration of s-block elements. Now, what are the characteristic properties of s-block elements? See children here, let us see the characteristic properties. So, highly electropositive and or soft metals with lower densities. So, these are highly electropositive and these are soft metals with lower densities. They are very good reducing agents. So, children, we are not going in detail, but in brief, let us see the characteristics of properties. In higher classes, we will know. So they are very good reducing agents. They have low melting and boiling points. So actually, these s-block elements are generally metals. These should have high melting and boiling points, but these are not having like that. These are having low melting and boiling points. They exhibit an oxidation state of +1 for first group and +2 for second group. That is, see here, this first group elements lost 1 electron. So that's why these are getting +1 oxidation state, and the second group elements losses here 2 electrons. That's why these elements get +2 oxidation state. Here children, one more children here. This helium actually it is kept in the 18th group, but this comes under s-block only, because if we observe the electronic configuration, here helium is with the 1s2 electronic configuration, means the last electron is entering into the 1s orbital, that's why it is s-block element only. But here actually this s-block s orbital is completely filled, so that's why it is having less reactivity. This won't lose or gain the electrons or share the electrons. That's why it is inert. That's why it is kept in the 18th group. But it belongs to s-block only. So the s-block elements are reactive, very reactive, and form ionic substances, except lithium and beryllium. See children here. Actually, this s-block elements losses the electrons. First group elements lost 1 electron. Second group elements lost 2 electrons. So like this, after losing electrons, they convert into ions. So using those ions, they form generally ionic substances. But here, except lithium and beryllium, these are having the covalent nature. Let us see in the next session. The metallic character and the reactivity increases as we go down the groove. See children here, top to bottom, the metallic character and reactivity increases. Because of high reactivity, they never found pure in nature. See children, already actually these are very reactive, because first group elements losses 1 electron easily, second group elements losses 2 electrons easily. So that's why these are highly reactive. So therefore they never found in pure in nature. They always found in the combined state with other elements like halides, sulfates, nitrates, carbonates, bicarbonates, so like that. They show characteristic colors in the flame. See how they show the characteristic colors. These are the characteristic colors properties shown by the s-block elements. Here lithium, when we expose to the light, when we expose it to the flame, it shows the scarlet color. Sodium gives golden yellow color. Potassium is lilac color, and rubidium is with red color, it burns. And cesium, it burns with blue color. So like that, calcium with brick red, and strontium with crimson red, and barium with apple green color. It burns. Next, children, the p block elements. Here the p block elements in which the differentiating electron enters in the p orbitals of the outermost shell are called p block elements. See, what are p block elements? The differentiating electron enters the p subshell. Then those elements are called p block elements. The group 13, 14, 15, 16, 17 and 18. So that is here group 3A to 8A are called p block elements. These elements are located on the right side of the periodic table. Already we have discussed. So here this is the periodic table, and these from 3A to 8A, these are the p block elements, or 13 to 18 group elements are called p block elements. The general electronic configuration of p block elements is NS2 NP1 to 6. Children, the general electronic configuration of p block elements is NS2 NP1 to 6. And here group 18 elements are called noble gases or inert gases. And group 17 elements are called halogens. And group 16 elements are called chalcogens. See children here, what are inert gases, what are halogens, what are chalcogens, actually why they are called so. Here this 18th group are called inert gases or noble gases. Why those are called inert gases? Because so these are having the completely filled orbitals NS2 NP6. So like that, these are having the completely filled electronic configuration, completely filled orbitals. That's why they don't lose or gain or share the electrons. So that's why these are called inert in nature and inert gases. And after the reactions, after the some reactions of here xenon, when we give some external conditions, means high temperature or high pressures, it reacts with a more elective negative element like fluorine and oxygen, and it forms some compounds with fluorine and oxygen combinedly. So after the reactions of this xenon, which are we previously known as inert gases, so these are named as noble gases. And this is 7th A group or 17th group elements are called halogens. So here halogens means, halo means here salts. Here salt generated compounds are called this halogen. These when halogens means the 7th A group elements reacts with these metals, they form salts. So that's why these are called halogens. And here is 6A group elements are called chalcogens. Why these are called chalcogens? Because here this, when the most of the ores of copper are in the form of oxides and sulfides. In Greek, this is called as chalco. So that's why these are called chalcogens. So let us see the characteristic properties of p block elements. The elements include all metals, non-metals and metalloids. So actually see children, the S block elements only metals, but here the p block elements include all metals, non-metals and metalloids. All gases, all gaseous elements are p block elements. So here except hydrogen and helium. So actually see children, in the periodic table we have 11 gases. Here this hydrogen is 1, helium is 2, this nitrogen 3, oxygen 4, fluorine 5, neon 6, here chlorine 7, and this bromine 8, this is argon 9, krypton 10, xenon 11. So among these 11 gases, this helium and hydrogen and helium are S block elements, and this remaining gases are p block elements only. So all gaseous elements except hydrogen and helium are p block elements. Most of these elements are highly electronegative and have high electron gain enthalpy. So what is electronegativity? What is electron gain enthalpy? Let us see in the next session, children. But these are, you remember that these are having most of the elements are having highly electronegative and have high electron gain enthalpy. Due to stable valence electronic configuration of 8th A group, that is NS2NP6, they are inert in nature. Already we have discussed, children. That's why these are called inert gases or noble gases. Some elements are good oxidizing and reducing agent. So, see, children, these p block elements, among these, so some elements are very good oxidizing and reducing agents. Generally, the right side of the periodic table elements are good oxidizing agents, and which are in the p block elements towards the left are called good reducing agents. Here, except group 18, these elements are very reactive, because already we know here 18th group is inert gases or inert group. So except this group, the remaining elements are very reactive. Now the next children, here the D block elements, which are also called as transition elements. Here what are D block elements? Let us see. The elements in which the differentiating electron enters the d orbitals of the penultimate shell are called D block elements. See, children, here. Hello. Hello, madam. Hello, madam. Hello. Hello, madam.
Sir, tell me, sir.
Is it okay, madam?
Yeah, it is audible, sir. Please
Okay.
continue, sir.
Okay, madam. Thank you. Thank you.
Okay, sir.
So, children, what are the d block elements? The elements in which the differentiating electron enters the d orbitals of the penultimate shell are called d block elements. Here, what is penultimate? And let us see in the next slide. Here are groups 1b, 2b, 3b, 4b, like that 5b, 6b, 7b, and 8b are D block elements. So what are D block elements? From first B to 8th B elements are called D block elements, children. These are in the middle of the periodic table in between S and P blocks. So these elements are located on the middle in between S block and P block elements. These are called as transition elements. The 3D, 4D, and 5D series are completely filled with 10 elements each. The 6D series is incomplete. So actually, children, these D block elements or transition elements consist of 4 series, that is the 3D, 4D, 5D, and 6D series. So among these, this is only 3 series, that is 3D, 4D, and 5D are completely filled with the 10 elements each. The remaining 6D series is incomplete. The general electronic configuration of D block elements is N-1D 1 to 10, NS1 to 2. Now let us see the characteristic properties of D block elements. See, children, here the elements are all electropositive and are metals. See, actually we have seen the S block elements are metals, but P block elements are having metals, non-metals, and metallites. But here the D block elements are only metals only. They are all solids except mercury, which is a liquid at room temperature. See, children, actually generally metals are present in the form of solid state. But here, except mercury, the remaining all solids, the mercury is in the form of liquid at room temperature. Now, the zinc, cadmium, and mercury, which are the second B group, have the electronic configuration N-1 D10 NS2. Here, what is the general electronic configuration of these elements? N minus 1 D 10 NS2. So these do not show most of the properties of transition elements. That's why children, these are not comes under the transition elements. So except these, the remaining all transition elements. Most of the elements possess catalytic activities. So children, in this slide, the characteristic properties which are shown here, these are very, very important in the IPE also. So many times they asked. So see here, what are the characteristic properties of D block elements? So like that, the question will come. See the answer here. Most of the elements possess catalytic activity. They form variable oxidation states. They form complex compounds. And they form alloys and interstitial compounds. And they mostly form colored compounds. And they exhibit paramagnetic properties. See children here. Number one is the catalytic activity. Number two, variable oxidation state. Number three is complex compounds, formation of complex compounds. Number four is formation of alloys and interstitial compounds. And number five is formation of color compounds. And number six is exhibits the paramagnetic properties. So these are the very important characteristic properties shown by the transition elements. The next one is the f-block elements. So these are also called as inner transition elements. Now let us see what are f-block elements. The elements in which the differentiating electron enters the f orbitals of the anti-penultimate shell. Now, just now already seen, we have seen in the D block elements penultimate shell, and here we are observing that anti-penultimate shell. Let us see in the next slide what is penultimate and anti-penultimate shells. So the elements in which the differentiating electron enters the f orbitals of the anti-penultimate shell are called f block elements. Here group 3 elements are called group 3b, group 3b elements are called the f block elements. These elements are located at the bottom of the periodic table. So we know very well from starting onwards we are observing this. Here, there are two series of f-block elements. So here the first one is the 4f series elements with atomic numbers from 58 to 71 are called lanthanides. So what are lanthanides, children? Here the 4f series elements with atomic numbers from 58 to 71. Here from cerium to lutetium are called lanthanides. Next, the 5f series elements with atomic numbers from 90 to 103 are called actinides. So like that, there are two series of f block elements in the periodic table. There is the 4f series lanthanides and 5f series actinides. The general electronic configuration of f block elements is n minus 2 f 1 to 14, n minus 1 d 0 to 1 and ns2. Now let us see the characteristic properties of f block elements, children. So these elements are heavy metals with high density and form colored compounds, complexes, interstitial compounds, and show paramagnetic property. These are the same like D block elements, children. They are naturally available in very small quantities. So that's why these are called rare earths. So why these f block elements are called rare earth elements? Because they are naturally available in very small quantities and are called rare earths. The elements after uranium. See children, actually the elements actually 90 to 103 are called here the elements 190 to 103. So those are called actinides. The elements after uranium means after 92, Z is called after 92 are called trans-uranium elements. What are those? Trans-uranium elements. Why these are called like that? Because these are synthetic. These are not naturally available. That's why these are called trans-uranium elements. Now, what are trans-uranium elements? The elements after uranium, that is with a atomic number greater than 92, are called trans-uranium elements because they are synthetic elements. They show a great similarity among themselves in their properties. Actinides are radioactive elements. So these elements are radioactive elements. These disintegrate the alpha, beta, gamma rays, children. That's why these are radioactive elements. Here the classification into types. Our next subtopic is classification into types. Here all elements are classified into 4 types. So here the first one is inert gas elements, and second one is representative elements. The third one is here type third is transition elements, and type 4 is inner transition elements. So like that, the elements are classified into 4 types. So here type 1 inert gas elements, representative elements, transition elements, and inner transition elements. So let us see one by one. Here the inert gas elements. So what are inert gas elements? Let us see. The elements in which the outermost S and P completely filled. These elements are called inert gas elements. So that is only group 18 elements are called inert gas elements. Why? Because only in this group 18, the outermost S and P subshells completely filled. In the remaining groups, so means the outermost S and P orbitals do not fill. That's why. So here, what are inert gas elements? Elements in which the outermost S and P orbitals subshells completely filled are called inert gas elements. Group 18 elements are called inert gas elements. The elements are here helium, neon, argon, krypton, xenon, radon. Here only these elements are having the valency electronic configuration here NS2 NP6. So that means here S and P outermost subshells are completely filling. The general electronic configuration of inert gas element is NS2 NP6 except helium. Here why except helium? Here helium is only 1s2. It is not having the p orbital. That's why here this is only exception. Except the helium, all are here the general outer electron configuration NS2 NP6. The presence of 8 electrons in the outermost shell is called octet configuration. See children here, what is the inert gas elements general electronic configuration? NS2 NP6. Here how many electrons totally? 2 plus 6, totally 8 electrons are there. So this 8 electrons which we call octet configuration, the presence of 8 electrons in the outermost shell is called octet configuration. The significance of octet explains the stability. Means when they are having the octet configuration, they are stable. They won't lose or gain or share the electrons with other elements. That's why they are inert in nature. So due to their low reactivity, here elements of group 18 are called as inert gases. Now the next type of elements is representative elements. Here what are representative elements? Let us see children. Here the elements in which the outermost S and P subshells are incompletely filled. See children, here we have to concentrate. For inert gas elements, the S and P subshells are completely filled. But for representative elements, the S and P subshells are incompletely filled. So these are called representative elements. Here the elements of group 1, group 2, a group from 13 onwards, 13 to 17. So these are called actually representative elements. Actually here S and P block elements are called representative elements, but except the 18th group. Here because 18th groups comes under inert gas elements, and except 18th group, this S and P block elements, that is 1 to 1 and 2 and 13 to 17, these are called the representative elements. All the S and P block elements except group 18 are known as representative elements. So in these representative elements, metals are present. So children, in this representative elements, so all are having here many non-metals are there, some metalloids are there, and some metals are also present in these representative elements. The next one is, the next type of elements is transition elements. So children, here what are the transition elements? The elements in which the ultimate, here ultimate means the last one. Here that's the nth shell, ultimate n, and penultimate. Now here we are observing the children, penultimate, that is the n minus 1 shell is called penultimate, or incompletely filled are called transition element. Once again I am repeating children, elements in which the ultimate and penultimate shells are incompletely filled are called transition elements. Here see the children, here the diagram I have given here. This is the, let us assume one atom, and this is the nucleus. This is the first orbit, second orbit, third orbit, fourth orbit. So like this, in this atom, let us assume 4 orbits are there. And this here the fourth orbit is called valency orbit or valency shell. And this is nothing but the nth shell. And this last but one is called n minus 1 orbit. And this is also nothing but penultimate shell. What we call penultimate shell. So when this nth shell and this n minus shell are incompletely filled, then that elements are called transition elements. The general electronic configuration of transition elements is n minus 1d, 1 to 10, ns 1 to 2. So next children, the inner transition elements or f-block elements. Here what are the inner transition elements? Let us see. The elements in which the ultimate, that is the nth shell, penultimate, n minus 1, and anti-penultimate, that is n minus 2 shells, are partially filled, are called inner transition elements. So children, once again I am repeating this one. So what are the inner transition elements? The elements in which the newly coming electron fills in the ultimate, penultimate, and anti-penultimate shells are partially filled are called inner transition elements. Here see children, here this is the ultimate shell, here is the nth shell. Here in this atom totally how many orbits are there? Here totally 6 orbits are there. This is the nucleus, first orbit, second orbit, third, fourth, fifth, and sixth orbits are there. And the sixth orbit is the ultimate shell or nth shell. And this fifth orbit is n minus 1, which we call penultimate shell. And here the fourth orbit is anti-penultimate shell, or nothing but n minus 2. You can call it as. So here children, the general electronic configuration of this inner transition elements is n minus 2 f 1 to 14, here n minus 1 d 0 to 1, ns2. Actually children, here what is for f orbital we can give n minus 2. Here why this f orbital we give n minus 2? Actually in the sixth period f orbitals are introduced. So already we have seen in the first session, the f orbitals are introduced in the 6th period and 7th period. Here, so f orbitals started in the 6th period. So that's why here, but we have only 4f orbital. Here 4f orbital is nothing but here, if we keep n is equal to 6, if we keep n is equal to 6, 6 minus 2 is nothing but 4f. So like that we can get the n minus 2 F, and also n minus 1. Here is the D. Why we give n minus 1 D? Here is the D orbital actually. In the fifth orbit it enters. So that's why we keep for fourth orbit it enters. If keep n is equal to 4, here we can get 3D. Actually we have 3D. That's why here for F orbital we have to give anti-penultimate shell, that is n minus 2, and for D orbital we give n minus 1, that's the penultimate, and for S and P we can give the nth shell, that is ns or np, like that. The next one is the metals, non-metals, and metalloids. So see children, one by one let us see. So what are metals? The tendency of elements to donate electrons and hence form positive ions is called metallic nature. So what is metallic nature, children? The tendency of elements to donate electrons, means the losing of electrons. So this is the metallic character. Now let us see, after losing of electrons, they convert into positive ions. See children, this is the equation. This is the metal after losing the electrons, it converted into positive ion. So this is the metallic nature. What is metallic nature? The donate of electrons, the tendency of donation of electrons. That is called the metallic nature. Metals have very less ionization potential values and more electropositive in nature. So this is also we can see in the next session, children, what is ionization potential and electropositive nature. Among the elements in periodic table, more than 78% are metals. So children, most of the elements in the periodic table are metals. Metals are usually solids at room temperature, here except mercury, already we have discussed. So they usually have high melting and boiling points. So children, generally metals are in solid state, they should have high melting and boiling points. So but here exceptions are there. Here the gallium is having low melting point, and cesium also having low melting point. Here the melting point of gallium is 303 Kelvin and cesium is with 302 Kelvin. Metals are good conductors of heat and electricity. So here children, because of lasting nature, they easily acts as good conductors of heat and electricity. In a group, metallic nature decreases. So children, from top to bottom in a group, the metallic nature increases. And in a period, metallic nature decreases. Children, the metallic nature in a period from left to right decreases. Next, let us see the non-metals. So what are non-metals? Here, this is just opposite to the metals. An element that lacks metallic properties and capable of forming anions, acids, acid oxides, and stable hydrogen compounds are called non-metals. So generally, this boron, carbon, nitrogens, these are good non-metals. Here, the equation is refers to the non-metals. Here, this non-metal taken the electrons and converted into anions. So in a group from top to bottom, non-metallic nature decreases and metallic nature increases. So what happens, children, here? The non-metallic nature in group from top to bottom, non-metallic nature decreases and metallic nature increases. In a period from left to right, non-metallic nature increases and metallic nature decreases. This actually we can see in the next session, children. Here why the non-metallic nature decreases in the children? Because here in a group, actually top to bottom atomic radius increases. So the losing nature of electrons increases, but the gaining nature of electrons is decreases. That's why the non-metallic nature decreases in a group, and metallic nature here decreases in the period. Next, metalloids. Some elements exhibit both metallic and non-metallic properties. Such elements are called semi-metals or metalloids. See children, actually here we have seen the metals and non-metals. But here some metals or some elements exhibit both metallic and non-metallic properties. So such elements are called semi-metals or metalloids. Here there generally metalloids are placed in the p-block elements. Examples are here germanium, arsenic, strontium, selenium, tellurium, etc. We will find while running diagonally across the periodic table. So children, so far what we have learned, let us see. Here, electronic configuration of elements on the periodic table, electronic configuration in periods, electronic configuration in groups, electronic configuration and types of elements, here S, P, D and F block. Here S block elements, P block elements, D block elements and F block elements. And the next one is classification into types, inert gas elements, representative elements, transition elements, inner transition elements. And the next one is the metals, non-metals and metalloids. So these are we have learned today's session, children. Now this is some exercise given to you for your practice. Just you go through the video once again and solve these problems, and along with some multiple choice questions. I have given the some long questions also here from 7 to 9. So thank you, children. Thank you, ma'am.
Thank you, sir.
And thank you, AD sir and JD sir. And thank you to Parandal.
Thank you, sir. Thank you. And dear children, here I want to mention one thing regarding the classification of elements into groups and periods. And this is based on the entering of differentiating electron into the orbitals, isn't it? Then do you find the difference between orbit and orbital? What is an orbital? The place where the probability of finding an electron is maximum is called as an orbital, isn't it? And then what is an orbit? It is a place around the nucleus where the electron revolves. So if the differentiating electron enters into the s orbital, the elements are called as s block elements. And then what is the maximum capacity of an s orbital? Means how many electrons it can accommodate. It can accommodate a maximum of 2 electrons, isn't it? That's why 2 groups are kept in s orbital. And please check out, right? So it's a task for you, children. So you please check out and let us know in our next session then how many groups are placed in p block, D block and F block, right? So it depends upon the maximum number of electrons an orbital can accommodate. Okay. And then today sir has very clearly explained you regarding the classification of elements into blocks and based on their chemical properties. So what are representative elements? See, what is the meaning of a representative? Who represents the properties? Means you will be seeing many medical representatives, isn't it? See, they will represent their company, isn't it? Like that. These representative elements include the S block and P block except the zero group elements, right? So they include the metals, non-metals and metalloids, right? And then coming to the inert gases. Why they are called as inert gases? Because of their inertness. See, they doesn't participate in the chemical reactions except xenon. And then transition elements. Transition means a change. See, we can see a change from metals to non-metals through this D block elements. That is a transition elements. And then inert transition elements. And how many series are placed in these inert transition elements? So sir has very clearly explained you regarding all these things. Please try to watch these sessions again and again and try to write down the notes, children. Okay, so we'll meet in our next session tomorrow. I thank Sampath sir for giving a wonderful session. Thank you, sir.
Thank you, madam. Thank you.
We thank each and everyone for giving us this great opportunity.